Hello, welcome to Chemistry with Dr. Clark. Today we would like to talk about calorimetry problems. A calorimeter is a piece of equipment used to measure the specific heat capacity of objects or the heats associated with chemical reactions. Okay, so the calorimeter that you are most likely familiar with is the coffee cup calorimeter. A coffee cup calorimeter, as its name states, is basically a coffee cup. Okay? Inside that coffee cup, you're going to put some water. Here's my water. And then you're going to place some sort of object. Now, the object could be just a chunk of metal. It could be chemicals that are going to react. It could be something that's going to dissolve, right? There's a lot of possibilities, and when we get to some problems, we'll see some. But usually what people start off with is they'll give you a chunk of metal. So the chunk of metal is usually quite hot. So it'll have an initial temperature. The container of water is usually about room temperature, pretty cool. And so what you do is you throw the chunk of metal into the water. Now, if you put a hot piece of metal in a cup of cool water, the temperature of the water is going to rise. The temperature of the metal is going to drop until they both end up being the exact same temperature. You would really like to measure the temperature, so you put a thermometer in. Because that way you'll know the initial temperature of the metal and you'll be able to tell me the final temperature of the metal. The water, you know the initial temperature of the water. You will know the final temperature of the water. Now, this is your experiment. This little piece of metal, you would have put it on a scale at the beginning, so you would have known its mass. And it's the same thing with the water. When you put the water in the cup, you would have measured its mass, so you'd have the mass of the water. If you have a temperature change and a mass, you can calculate the heat. Q equals mc delta T. So you can calculate the amount of heat here. And the same thing down here. You can calculate the amount of heat. Q equals mc delta T. And the really nice thing about this is that a calorimeter follows the law of conservation of energy. The amount of energy in the universe can't be created or destroyed, but it can be moved from one place to another. So all of the heat that was hiding here inside of this piece of metal because it was really hot, a lot of it gets transferred to the water. So the amount of heat, the Q, that's going to be lost by the metal is going to equal Q, the amount of heat absorbed by the water. Right? So the two Qs are the same. And what makes this setup beautiful is that this is water. We know the specific heat capacity of water. It's 4.18 joules, grams, degrees Celsius. Now, if you're doing a course where you are learning about calorimetry, water is our favorite substance to be put here that'll absorb or release heat. And so the specific heat capacity of water gets used a lot. It's worth memorizing. Okay, it's worth memorizing that the specific heat capacity of water is 4.18. So if you know the initial and final temperature of the water, you know the mass of the water, you know the specific heat capacity of the water, you can calculate the Q. If you know that the Q absorbed by the water is equal to the Q given off by the metal, you would know this. You know the mass because you can weigh it. You know delta T because you can measure initial and final. It allows you to calculate the specific heat capacity of the metal. Right? We like to use calorimeters to figure out specific heat capacities of metals. And you can see on this page, I've got a whole table of them, right? Somebody did the experiment and found that the specific heat capacity of, say, chromium was 0.449 joules per gram degree Celsius, right? So these are calorimetry questions. They use this type of calorimeter or perhaps something a little more sophisticated. Now, if you didn't watch the video on calculations with heat capacities, which specifically focused on this formula, you might want to go back and take a look at that one because those problems only involve using this equation once. When you're talking calorimetry problems, you're often talking about using it twice. Once for the water and once for the object that's being placed in the water. Okay, so you really want to be familiar with using this equation first before you move into these type of calculations. Okay, so let's say that we would like to try some problems. So a typical problem here does talk about a piece of metal. It says you've got a 25-gram sample of metal heated to 100 degrees and then dropped into a beaker containing 90 grams of water at 25 degrees. Temperature of the water rises to a final temperature of this. What's the specific heat capacity of the metal? Now, I like to do this in steps. If you're going to be doing a calorimetry problem, your step number one for these problems will always be the same. Step number one is always going to deal with the water. Now, let me cover up the second problem so we have lots of space. Okay, in a calorimetry problem, your first step is always going to be water. So maybe we should say that. Step number one, deal with the H2O. And your step number one is always going to be Q equals mc delta T. Always. Now, the problem with this is that you've got both water and a metal. So you've got two masses, you've got two initial temperatures, you're going to have two specific heat capacities. You've got to keep your numbers straight. Okay, so for this calculation in water, Q mc delta T, which is final minus initial, I'm going to go through the problem and pick out the ones that go with the water, and only the water. So the problem says you have a 25-gram sample of metal. That's a metal number, so I'm going to skip it. The metal was heated up to 100 degrees. That's a temperature that goes with the metal, so I'm going to skip it. It's dropped into a beaker containing 90 grams of water. Okay, that's a water number, and the water is at 25.32 degrees. Okay, so that gives me some water numbers here. 90 grams would be a mass, and the water's at 25.32. Now, that's before you drop the metal in. So this would be an initial temperature. So the initial temperature of my water is 25.32. It says the temperature of the water rises to a final value of 27. Okay, so that's the final value of water. So 2718 degrees Celsius. And it asks for the specific heat capacity of the metal. Okay, that's a metal number. I'm not worried about it. In step number one of these problems, you always are given the specific heat capacity of water, even though the problem doesn't usually give you the specific heat capacity of water. It's one of those, I give it, but I don't really give it, right? You really have to memorize the 4.18 joules, grams, degrees Celsius for the water, right? It's considered a given, but it's not often actually given. And for step number one, you are always calculating the amount of heat that goes with the water. Always. Now, your units have to be consistent. The mass is in grams. The specific heat capacity has grams. The temperature is in degrees Celsius. The specific heat capacity has degrees Celsius. The specific heat capacity has joules. Therefore, when I calculate the heat, it'll be in joules. So let's take my numbers, put them in my calculation, and calculate my heat. So Q is going to be the mass, 90 grams, times the C, 4.18, times the temperature, which is 25.32. So my Q will be, let's pull out my calculator. Almost made a mistake. I just pulled out my initial temperature. I forgot to do my delta T. Ooh, that would have caused me a lot of trouble later. Okay, so 2718 minus 25.32. 1.86. All right, so this really should be 1.86. It is one of those things that when I write down my temperatures, normally I try and do my subtraction first because I know that personally, forgetting to do delta T is one of my issues, right? So when I do these problems, that's something that I know causes me some issue. So it's something that I have to watch out for. It's the reason why practice is really good with these, because you'll learn the things that you do well, you'll learn the things that cause you issues, and so that way you can always be watching out for them. Okay, so let's do this calculation. That'll be a 90 times 4.18 times 1.86 gives me an answer of 699.7. 699.7 joules. Now, if you'd wanted to leave all of your units in and cancel numerators and denominators, it'll still give you joules. It does depend on the person that's getting you to do the problems. Sometimes they don't mind unless you put as long as you put the right unit at the end, you're good. Sometimes they will require you to have units all the way through, right? So whatever's asked for, that's what you got to do. Now, if we do stop for a minute and talk significant figures. When you're doing a subtraction, when you're doing a subtraction, it's all about the least number of decimal places. So if this has 2 decimal places and this has 2 decimal places, then your temperature here should have 2 decimal places, which it does. When you're doing multiplication, it's all about sig figs. So 90.0 has 3 sig figs, 4.18 has 3 sig figs, and 1.86 has 3 sig figs. It's kind of a classic standard, right? When you're doing science, we do tend to do things with 3 sig figs. So my answer should only have 3 sig figs. So for my answer, I like the 6, I like the 9, I like the 9, but I really want to get rid of that 0.7, right? Because I would like to have only 3 sig figs. So my Q should round. Now, the first number I'm getting rid of is bigger than 5, so it rounds up. So 699 becomes 700 joules. Quite a nice number. Now, when we do these problems, the first step in every single one of them is going to be dealing with the water. Step number 2 is always the same as well. Okay, step 1 is always deal with the water. Step 2 is always change the sign of Q. And the reason for that is this is the Q related to the water. The water got hotter, right? It went from 25 degrees up to 27. It got hotter, so it absorbed heat. It absorbed 700 joules. And we know that if you're absorbing heat, if it's endothermic, your heat is positive. But now if we think about the perspective of the metal cooled down, right? It started at 100 degrees and it's going to cool down to 27. It's giving heat away. It's exothermic. So from its point of view, this heat should be negative. And the last part of my calculation is going to focus on the metal. So what I need to do is change the sign because the Q for the water may have been 700 joules because it absorbed it. The Q for the metal is going to be a minus 700 joules because your metal lost the heat. Okay, with a calorimetry problem, the second step is always a sign change. If the water absorbs heat, the system, the metal, the chemical reaction, whatever it is, had to lose the heat. So there's a sign change. Now, step 1 and step 2, rock solid. Step 1's always the same. Step 2 is always the same. Like they never change. The problem is step 3. Step 3 depends on the problem. Okay? Different problems will require different step 3s. That's why I got a couple of problems to do. If the problem says, what is the specific heat capacity of the metal, what you threw in, then basically you're going to do Q equals MC delta T again, but this time you're going to do it for the metal. Okay, if the problem asks for something different, your step number 3 will be different. Okay, so let's fold this down and give ourselves some room. Okay. Now, if I'm going to do this calculation again, in step number 3, I'm going to do it for the metal, which means that I'm looking for a Q, an M, a C, a delta T, but this time it's all for the metal, not for the water. So if we come back here, remember how we started out with a 25-gram sample of metal and we skipped that number because it was a metal number? Now we get to use it. So I have 25 grams, which is a mass, and it says it was heated to 100 degrees. Now, this always causes people problem because when I say the metal was heated up to 100 degrees, that really feels like a final temperature, right? I'm heating it up to 100. But for this type of problem, classically, water in the cup is cool, metal is hot, metal gets thrown into the cup. you need to have metal that is hot at the beginning. So in order to make it hot at the beginning, you got to warm it up. So the words here are a little misleading, right? Because it says that it was heated up to 100. So it kind of feels like it's a final, but it's not. In this problem, it's heated up to 100, and that's the start of the experiment. So my initial temperature here is the 100 degrees. The other thing that's a little misleading in this problem is that the problem will say the temperature of the water rose to a final value of 27. Right? It specifically tells you the final temperature of the water, but it never mentions the final temperature of the metal, right? If you read through, there is no talk of final temperature of metal. That's because they think you're smart people, right? They know that you know that if the metal and the water are in the same place, then they have to be the same temperature. So when it says that the final temperature of the water is 27, that's also the final temperature of the metal. Now for this one here, because the metal is cooling down, you are going to get a negative change, right? 27.18 minus 100 gives me a minus 72.82, which is okay, right? I've got a negative heat for the metal, so it only makes sense that I get a negative delta T for the metal, right? The two negatives go together. Now for sig figs, I did miss a 0, right? This should be 100.00. 2 decimal places, 2 decimal places, 2 decimal places. Okay. Now the problem does say, what is the specific heat capacity of metal? So I'm looking for this. And the heat comes from here, because the amount of heat absorbed by the water is equal to the amount of heat given off by the metal. So that'll be a minus 700 joules. Okay, so I'm back to the point now where I just need to take all my numbers, dump them in my equation. Now, there's two schools of thought on this. You could put all the numbers in and then rearrange the equation as you do the math, or you can rearrange the equation first. Okay, I'm going to rearrange the equation first. So if I'm looking for C, because the M and the delta T are multiplied, to get rid of them, I'm going to divide them. So the M will move to the other side as a division. The delta T will move to the other side as a division. There we go. So let's put our numbers in. This is a minus 700. Now, that is in joules. The mass is 25.0 grams. And the temperature is a minus 72.82 degrees Celsius. Gives me my C. Now, if you look at it, you got a negative in the numerator and a negative in the denominator, so they will cancel out. That's perfect. And you are dividing by two different things, right? So it's 700 divided by 25 times your 72. You're either going to have to use brackets in your calculator, or this 700 is being divided by the 25, but it's also being divided by the 72. So you could divide twice, right? I can say 700 divided by 25 divided by 72.82. And that gives me a value of 0.3845. And the units are all here. Joules in the top, grams and degrees Celsius in the denominator. That's the specific heat capacity of your metal. Now again, if you're doing sig figs, 700 has 3, 25.0 has 3, 72.82 has 4. You always go with the least, so this number should have 3. The 0 in front don't count, because I really could have left it out and just said 0.3845, and you would know what I meant. So for this one here, if I'm going to do 3 significant figures, I like the 3, I like the 8, I like the 4, I'm going to get rid of the 5. So if you're going to get rid of the 5, that means you round up. So this would be 0.385 joules, grams, degrees Celsius is the specific heat capacity. Okay, 3 steps. First 2 are always the same for every problem. Step 3 depends. Now, it does ask me at the very end, so you found the specific heat capacity of the metal. What metal is it? Well, that's why I have my chart way back here in the beginning, right? If I look at my chart, I'm looking for a metal that has a specific heat capacity of 0.385. So if I look through, copper has a 385. Anything else have a 0.385? 385. I got a 387. Now, to be honest, if you're making measurements, there's always a little bit of error involved. So I would say I'm pretty sure it's copper, but there's also a fairly good chance that it's zinc, right? So if they ask you to identify the metal, you'd have to say copper, but also maybe zinc. Now, let's say that you actually did the experiment. You're the person who had the cup, you're the person who had the metal, you're the person who threw it in. Would you be able to tell the difference between copper and zinc? Yes, because copper is penny color, right? The old pennies were made out of copper, so it's sort of a red-brown. And zinc is kind of a silver color. So if you had it in your actual hand and did the experiment, you'd be able to say, oh, when I started off, this was reddish-brown, so I know it's copper. Or, oh, when I started off, it was kind of a silver color, so I think it's zinc. Right? But it does allow you to narrow it down to hopefully one metal, but sometimes more than one. All right, so problem number 2 here is exactly the same, so let's just skip that one for now and move on to number 3. Number 3 says Coke, which in the world of chemistry is just another way of saying carbon. So you got a block of pure carbon, is used to refine metals. It's burnt to heat a kilogram of water. 5 grams of Coke raise the temperature of the water from 10 degrees to 47. Calculate the heating value. Okay, so the Coke itself, if we talk about the reaction, let's say you're trying to refine iron. So you'd have this big cauldron of iron, it's melted, and you throw in the Coke. Well, the carbon reacts with all of the impurities. So if there was like an oxygen impurity, it would react with the oxygen, form carbon dioxide, and it just disappears, right? Because gases escape. So that's how it's used, right? It's used that way. But in this particular problem, that's just the backstory, right? I don't really care that it's used to refine metals. What I really care about is that I'm going to take it, I'm going to burn it, and I'm going to heat up some water. Okay, so again, this is a calorimetry problem. Now, the calorimeter would have to be a bit more sophisticated than the coffee cup, right? Because you can't burn something in a cup of water. So for this one here, you still have your cup of water, but what you do is you put a metal box inside that's waterproof. You put your little pile of carbon here, you dump in some oxygen gas, and you burn it in the box. Now, if you're burning something in the box, that's going to produce a huge amount of heat. Where's that heat going to go? That heat's going to go into the water. Okay, so you're still taking heat and moving it from the system to the surroundings, from the system to the water, right? So just like in the last problem, the water is going to absorb all of this heat. So it's a calorimetry problem. In calorimetry problems, step number 1 is always about the water, always about our H2O. So we're going to do Q equals MC delta T for the water. So I need to know the Q, the M, the C, the delta T, which is final minus initial. Okay, so if we look at our problem, we're going to pull out numbers that are related to water. So we are going to heat up 1 kilogram of water. Okay, so my mass is 1 kilogram. Not super liking that a whole lot, mainly because when we do these problems, masses tend to be in grams rather than kilograms. So I may have to, whoops, sorry, that's a kilogram. There we go. I may have to switch that out. Okay, but it's not a hard switch, but it's something that I have to be aware of. Now I have 5 grams of the Coke. That's not water, so I'm going to ignore it. And the temperature of the water is going to go from 10 to 47. Initial temperature, final temperature. Okay, so my final temperature of the water is 47. The initial temperature is 10. So 47 minus 10 is a nice 37. 1 decimal place, 1 decimal place, 1 decimal place. Now, for step number 1, you are always looking for the Q, always. So in step number 1, you always have the C, because it's water, right? You've memorized it. So that's 4.18 joules, grams, degrees Celsius. And you can see here, this is where my problem comes in, because I've memorized this as joules per gram, and I'm given a mass in kilograms, right? So that's a bit of an issue. So if I was going to do this, I'm going to switch this into grams, which means I'm going to multiply by 1,000. So instead of 1.00, if I times it by 1,000, I'm going to end up with 1,000 joules. Okay. Sorry, did it again. It's 1,000 grams. Just too many heats, got joules on the mind. Okay, so we have everything. Let's substitute it into my equation. So my mass is 1,000 grams. My specific heat capacity is 4.18 joules, grams, degrees Celsius. And my temperature change is 37 degrees Celsius. Sorry, it got kind of squished. Now, the last time I don't think I wrote down any of the units. I just said, hey, if this is in joules, my heat's going to be in joules. But this time I wanted to put them in to show you cancellation. Right, I've got a gram here in the numerator. I've got a gram in the denominator, right? This is per gram. Numerator gram, denominator gram, cancel. I've got degrees Celsius in the denominator. I've got degrees Celsius in the numerator, right? They'll cancel. So the only unit I'm going to have left is just the joules. So if we pull out our calculator, that's 1,000. Whoops, not plus. 1,000 times 4.18 times 37.0. Gives me a lot of heat. 1,54660 joules. It's like 154,660 joules. That's a lot. Now, normally I would just leave it as joules. But since it's a really big number, I'm kind of thinking I'd like to turn it into kilojoules just to make the number easier to deal with. The other reason why I'm thinking that I should probably turn it in kilojoules is because I read to the end of the problem, it does say calculate the heating value in kilojoules per gram, right? So it's telling me that eventually they would like it in kilojoules because it is such a big number. So when we had kilograms and we wanted to turn it into grams, we times it by 1,000. If you want to turn joules into kilojoules, it's like going in the opposite direction. You're going to divide by 1,000. So your Q would be 154.660 kilojoules. Now, this also makes significant figures a whole lot easier. Right, if I look through my numbers, the original 1.00 kilograms had 3 significant figures. The 4.18 had 3 significant figures. And when I subtracted, my temperature had 3 significant figures. So if I want to round this to 3 significant figures, I like the 1, I like the 5, I like the 4, but I'm getting rid of everything else. Since the thing I'm getting rid of is bigger than 5, it'll round up. So I will have a heat of 155 kilojoules. Nice number. Now, the water warmed up because the water absorbed heat. So from the water's point of view, this was an endothermic reaction. But from the Coke's point of view, it was being burnt. When you burn things, they give off heat. That's an exothermic reaction. That's why we got to do a sign change. Remember, step number 2 is always going to be a sign change. So if the Q for the water was 155 kilojoules, then the Q for the Coke is going to be a minus 155 kilojoules. Right? You got to have a sign change. Because if you burn something, that's exothermic. It's giving off heat. Step 1 and step 2, always the same. Always. Step 3 is the one where you have to go with the problem. Now for this particular problem, they're not actually asking for a whole lot more. Basically, the problem is saying, please calculate the heat in kilojoules per gram of Coke. They're telling me that they want it in kilojoules per gram of Coke. Well, I got the kilojoules. That's a minus 155 kilojoules right there. How many grams of Coke did I have? Problem told me I had 5.00 grams. So 5.00 grams of Coke. If we do the division, 155 negative divided by 5.00 gives me a minus 31. Kilojoules on the top, grams on the bottom, so it's kilojoules per gram. Now, if we talk significant figures, this one is like opposite to everything else we've done. Normally, you have to chop your number off to make it have the right number of sig figs. This one you got to make bigger, right? 155 has 3 sig figs. 5.00 has 3 sig figs. 31 only has 2. I need to put a 0.0 at the end to give it 3 significant figures. Now, it is negative because, like I say, it is a exothermic reaction. Okay, so step 3 sometimes can get changed up a bit. All right, so I did have a second problem like that, but I think we're good. We'll skip that one, and we'll move on to like the third type. Okay, so the first type was just a metal being thrown into some water. The second type was something being burnt. The last type is a chemical reaction. Now, first 2 steps are going to be exactly the same. Third step is going to be a little bit different. Now, the way this one's going to work, you have your container, but because you're mixing chemicals, the chemicals usually come pre-dissolved in water. So in the beginning, your cup doesn't have any water in it. When you add your first chemical, you're going to add some water. When you add your second chemical, you're going to add more water, right? So let's talk about what we're adding. You've got 25 milliliters of water containing 0.025 moles of HCl at 25 degrees. Okay, that's your first chemical. Then you're going to add 25 milliliters of water containing 0.025 moles of sodium hydroxide, also at 25 degrees. Now, for these problems, they do tend to give you some numbers that you don't really need. Like for the HCl and the sodium hydroxide, this is an acid-base neutralization. It's a double displacement, right? The HCl and the sodium hydroxide will react. The Na and the H will switch places. So you'll end up with water and sodium chloride. The only reason why the problem tells you how many moles of each one you have is so that you know that there's just enough of both for the reaction, right? This is a 1-to-1 reaction. For every 1 HCl, there's 1 sodium hydroxide. So for every 10 moles, you'd need 10. For every 6 moles, you'd need 6. For every 0.025 moles, you'd need 0.025. Okay, the only reason why the moles are there is to tell you that you have the perfect amount. For this particular problem, you don't actually need to know the moles or the identities. All that really is important is the temperature, because that's your initial temperature, and the volume. Now, water is really cool. Like they've put the assumption here at the end, assume the densities are 1 gram per milliliter. At room temperature, if you have 1 gram of water, it takes up 1 milliliter of space, right? The two of them are the same. So when I say you have 25 milliliters of water, it's like saying you got 25 grams of water. When I tell you you've got 25 milliliters of water over here, 25 grams. So in the end, how much water do you have in this cup? I've got 25 grams from the first solution, and I've got 25 grams from the second solution. So I've got a total of 50 grams. The water here was 25 degrees, the water here was 25 degrees, so when you mix them, your temperature's still going to be 25 degrees, right? Because they're both 25 at the start. Now, it says calculate the enthalpy change in kilojoules during this reaction if the highest temperature recorded is 32. So when you mix them together, the chemical reaction happens. It is exothermic. And where does all the heat coming out of the chemical reaction go? It gets sucked up by the water. So the water started at 25, but the water is going to finish at 32. Okay? So for this problem here, like all the rest, step one is all about the water. Step one is your H2O, and you're going to do Q equals MC delta T. Well, sure, I've already got pretty much everything, right? If I do delta T, T final minus T initial, 32 minus 25, that would give me 7 degrees, oops, 7.0 degrees Celsius. 1 decimal place, 1 decimal place, 1 decimal place. Almost forgot. I got my mass. We know that the Q is the question mark, right? Step one. And we know that the C for water is something that we've memorized. 4.18 joules grams degrees Celsius. So all I need to do is take all those numbers and dump them into my equation. Now, I don't want to carry my units. So as long as they all match up, I'm good, right? Celsius and Celsius, grams and grams. So if this is in joules, my heat is going to be in joules. Okay, so let's put them in. Mass is 50.00. The C is 4.18. And the temperature change is 7.0. So if I put those together, I've got 50 times 4.18 times 7. Gives me 1,463. And I anticipate the units will be joules. Now, if we are going to do significant figures, this one's a bit of a mixture, right? 50.00 has 4, 4.18 has 3, and 7.0 has 2. And you always go with the least. Okay, so I need to chop this off at the 14. Because the number is big, I should turn it into scientific notation. So 1.463 times 10 to the power of 3. Right, I moved the decimal 3 places. 1, 2, 3. That's why there's 10 to the 3. And if you want two significant figures, 1, 2, you're chopping those off. So the thing that you're chopping off is bigger than 5, which means you round up. So my Q will be 1.5 times 10 to the 3 joules. Now, can I tell you a secret about chemists? We really don't like scientific notation. Scientific notation, we can do it, but it's not our favorite. So what about if we kind of ignore this for a minute and go back to the 1,463 joules. We may not like scientific notation, but we love unit conversions. This is a pretty big number. What about if instead of leaving it as joules, I turn it into kilojoules? Right? I can turn it into kilojoules by dividing by 1,000. So that would be 1.463 kilojoules. Now, if I've turned it into kilojoules, isn't this nice and easy to round off to 2 sig figs, right? If I chop it off there, number I'm chopping off is 6, just like before, so it's going to round up. And I don't have to worry about scientific notation because this is not a big number anymore, right? By turning it into kilojoules, I've turned it from a big number into a smaller one. That's what we like to do as chemists. So my Q here would really be just 1.5 kilojoules. Those two answers are the same, because what does kilo mean? Kilo means 1,000. This is 1.5 times 10 to the 1,000 joules, right? 10 to the 3 is 1,000. So instead of saying 10 to the 3, I've got in a kilo. Okay. Now, step number 2, also always the same. change the sign. Because if the Q for the water is 1.5 kilojoules, then the Q for the reaction has got to be the opposite, right? If the water sucked in or absorbed energy, that means the reaction had to give it off. So the reaction is a minus 1.5 kilojoules. Step 1, step 2, always the same. Now, if we go back to the problem, let me go back. Step number 3 always depends on the problem, right? First one, we found that if it was a metal, we had to do MC delta T a second time. Problem number 2 is a little easier, right? Because I wanted to have it as energy as kilojoules per gram. So I just had to take the kilojoules divided by the grams, right? It was a small thing at the end. This one's better. It's asking for the enthalpy change. All I need to do is change my symbol. Q is a symbol for heat. The symbol for enthalpy change is delta H. Okay, that's it. Q is for heat. Delta H is for enthalpy change. That's enthalpy change. So really, to get this answer as an enthalpy change, I just need to change the symbol. So instead of a Q equaling 1.5 kilojoules, I have to write it as a delta H equals the minus 1.5 kilojoules. Right? This problem is the best because in the end, it's just the symbol change. That's all. Now, you do actually have to write down the delta H because if you leave it as a Q, that means heat. Doesn't mean enthalpy change. Right? So you have to change it to the delta H. But those are the 3 major types of calorimetry problems. Metal, something being burnt, or some sort of chemical reaction. I wish you the best of luck with your calorimetry calculations, and thanks for joining me with Chemistry with Dr. Clark.